Good afternoon, everyone. Sorry I can't be there with you this afternoon. I had some last-minute math meetings that I had to attend, but I will be available for help at lunch tomorrow if you have any questions that you want me to go over with you before the test. So today we are reviewing our polynomials part 1, so the first half of our polynomials unit. And we're going to review the key things that you need to go and look at a couple of examples. So the first thing is our key features of linear and quadratic functions. When we did and reviewed linear and quadratic functions, we did a lot of rearranging the equations. That won't be tested on the test tomorrow. The key things that I want you to know for the test tomorrow is just the key features and be able to pull out the information, pull out those key features from the equations. So let's review what those key features are. So for linear, we know that it has the form of y equals ax plus b, or the more commonly known one, which is the one that we talked about, is y equals mx plus b. And remember for that one, we know that m is equal to the slope and b is equal to our y-intercept when it's in that form of the equation. When we look at a graph of a linear equation, we know that it is a straight line on our graph. And then our key features of our graph, we have our slope, which we already talked about is our m in this equation. We have our y-intercept, which again we already talked about is b in this equation here. And then we also have an x-intercept. And remember, we just find the x-intercept by plugging in y equal to 0. The last thing is the domain and range. Remember, because it's a straight line, it just continues on in both directions. So there are no restrictions on x or y. So we can just say that our domain is that x is in the reals. And same for the range, because again, there's no restriction on y since it continues in both directions, up and down. So our range is also that y is in the reals. And that's true for any linear equation. It's always that domain and range are in the reals for linear equations. The second is the quadratic. Remember, it has three forms. We have our standard form, which is when it's y equals ax squared plus bx plus c. Oops. We have our vertex form, which is when it's ax minus h squared plus k. And we also have our factored form, which is when it's ax minus s bracket x minus t. So those are the three forms that we often see quadratics are in. Now in those three forms, we can pull out key information from each of them. And we'll talk about that a little bit further down here. First off, what do we call a graph when it's shaped? When it's a quadratic, when it's graphed, we know that it is a U shape. And remember, we call that a parabola. So it's called a parabola, and we know it's a U shape when it's quadratic. And key features of our parabola include the vertex, which we can see down here. Our vertex is equal to the h value. And remember, when it's taken outside of the brackets, the sign changes. So if it's negative inside the brackets, it's positive outside the brackets. And the k value, and that comes from our vertex form. Another key feature are our x-intercepts. And remember, those can also be called zeros or roots, and they all mean the same thing. They all just mean the x-intercepts. And remember, our x-intercepts can easily be pulled out from our factored form, and it's the values of s and t. But again, because they're inside brackets, when you pull those values out, the signs switch. So if this was a negative s, when we pull it out, it would be a positive s. If this was a positive t inside the bracket, outside the bracket, it would be a negative t when we pull out those x-intercepts. And the last key feature that we like to pull out is our direction of opening from each of our equations. And in this one, it doesn't matter which form of equation it's in, we can always determine what the direction of opening is. And remember, that's always just the sign of the A value, so the value that sits out front. So if A is positive, we know that our parabola will open up. And if A is negative, we know that our parabola will open down. So those are our key features of linear and quadratic functions. Let's take a look at an example of just pulling out some of those key features. So we'll go to our examples at the bottom here. So we're given this equation here. We're asked for the slope and the y-intercept. So remember, the slope in our equation is always the one that's sitting in front of the x. So our slope in this one is -2. And our y-intercept is always the one at the end. So our y-intercept in this case is +1. In the factored form, we're asked for the x-intercepts and which direction it opens in terms of our parabola. So our x-intercepts, because we have x -4 in the brackets, remember when we take it out of the brackets, the sign switches, so that becomes a +4. And our other x-intercept is the 3 that's inside the other bracket, but because it's a positive and we pull it outside the bracket, it becomes negative. So our two x-intercepts are 4 and -3. And then we need to decide which direction it opens. So in this case, we look at our A value out front. It is a positive value, so we know that our parabola opens up. Now our last one here, this one is in the vertex form, so we're asked to pull out the value of the vertex. And remember, the value of the vertex, we get our x value from inside the bracket with the x, so because this is a -5, when we pull it outside the bracket, it becomes a +5. And then our y value of the vertex is always just the last term at the end, which in this case is -1. So our vertex is the point 5, -1. And again, for the parabola, we're asked whether the direction of opening, so whether it opens up or down. For this one, again, we look at our A value. In this case, it's a -7. So because the A is negative, we know that our parabola opens down. So those are the types of questions that you'll be expected to be able to answer on your test tomorrow about linear and quadratic functions. The next thing that you need to be able to do is you need to be able to identify the degree of a function from an equation. Remember, we identify the degree of a function from an equation by looking for the highest degree of the variable. So we look for the variable that has the highest exponent, and then that is our degree of the function. So let's look at some examples here. We're asked to determine the degree and the leading coefficient. And remember, the leading coefficient is just the value, the number that sits in front of the variable that had the biggest exponent. So in this example here, we're looking for the variable with the biggest exponent, which is this one here, x to the power of 6. So we know that our degree then is 6. And for the leading coefficient, it's just the number that's sitting in front of that variable. So whenever, remember, there's not actually a number sitting in front of the variable, there's actually a 1. So we know that our leading coefficient's a 1. So we know that our leading coefficient's positive. And remember, the real key thing about leading coefficients is whether they're positive or negative, not whether they're what the number actually is for us right now. Let's take a look at our second example here. Again, we're looking for our degree, so we look for the variable with the biggest exponent, which is this one here. So we have a degree of 3. And our leading coefficient, remember, is the number that's sitting in front of that variable, which in this case is a -2. So our leading coefficient is then a negative value. Something else that we need to be able to do with our polynomials is we need to be able to know and be able to identify the following polynomial functions. These is either from the graphs, so you'll be able to identify this information from the graphs, or you should also be able to identify this information from their equations. So the first thing is our end behaviors. Remember, end behaviors are based on what the degree is, whether it's an odd or an even, and what the sign of the leading coefficient is. Remember, when it's an odd function, so when our degree is an odd value, we know that our end behavior is always going to be diagonals. So it's always going to be 3 to 1 or 2 to 4. It always has to be diagonals. And remember, we number our quadrants by starting at that one and moving around in this direction. So sometimes if you're getting confused with this, it might help for you just to draw a little diagram like this on your page, and that can help you just visualize your quadrants. So for odd, we always know it's diagonal, so it's got to be a diagonal across this way or a diagonal across this way. And remember, when we're reading our end behavior, we always move from the left of the graph to the right. So we always read from left to right on our graph. And then it depends on whether it's positive or negative as to which diagonal we use. So when the leading coefficient is positive, that's always the diagonal of 3 to 1. So positive is our regular one of 3 to 1. When our leading coefficient is negative, but it's an odd, it has to be the diagonal of 2 to 4. For our even degreed function, so that's whenever our degree value is an even number, we know that our end values, our end behaviors, have to be in the same direction. So they either both have to be up or they either both have to be down. And for this one, the rule is very similar to our parabolas. When our leading coefficient is positive, we know that it opens up. So when something opens up, it goes from quadrant 2 to quadrant 1. When our leading coefficient's negative, it opens down. And opening down is the quadrants 3 to quadrant 4. And remember, you need to have these rules memorized, so please make sure you're studying those. Let's take a look at some examples here of determining our end behavior based on the degree. So from our previous example, our first one, we had an even degree because it was a degree of 6. And our leading coefficient was a 1, and it was a positive 1. So because it's an even degree and it has a positive leading coefficient, that means that our polynomial, it opens up. So it has to go from quadrants 2 to quadrants 1. For the second example that we did on the previous page, we had a degree of 3. So our degree is then an odd value. And we had a leading coefficient of -2. So we had a negative leading coefficient. So it's an odd degree with a negative coefficient. And when it's odd, we know it has to be diagonals. And because it's negative, it has to be the diagonal of 2 to 4. Something else that we need to be able to identify is the number of turning points. Remember, the number of turning points, the relationship is that it's at most one less than the degree. So remember when we were discovering about turning points and our degree functions, our number of turning points was always one less than whatever our degree was, at the very least. It could be more or less than what our degree was, but it has to be at least one less than our degree. So again, looking at our previous example, if our degree for number 1 was 6, we know the most amount of turns that our graph can have is then 5, because it has to be at least one less than a number of degrees. Similarly, for example, number 2, we had a degree of 3. So again, the most amount of turns that we can have in our graph is 2 turns, because it has to be one less than the amount of the degree. Oops. Remember, that works the other direction. When I give you a graph and you count the number of turns, you know that the least degree that it can have is one more than the number of turns. The last thing that you should be able to identify, and this is just from the graphs, is whether the graph has a point symmetry or a line symmetry. Remember, point symmetry is when you can choose a point on your graph and you can rotate the graph at that point, And as you rotate it around, if they match up, then it has point symmetry. For line symmetry, remember that's if you can draw a vertical line down the middle of your graph at some point. And if you draw a line down the middle, then it's the same on both sides if you fold it over that top of that line that you drew. And that's when you have line symmetry. And remember, there are some graphs that don't have point or line symmetry, and for those ones, you would just say that it has no symmetry at all. Let's take a look at some examples of graphs. So for these graphs here, we're asked to determine the least possible degree and whether it's even or odd, the end behavior, the sign of leading coefficient, and the type of symmetry if it has any. So let's take a look at graph A here. So the first thing we need is the least possible degree, so we need to count the number of turns. So we have 1, 2, 3, 4, 5, 6. So there is 6 turns. So we know that the least possible degree that it can have is 7. And because we know the least degree has to be 7, we know that that's an odd value. Another way that we know that it's odd is because our end behaviors, they end up in diagonal quadrants. It goes from quadrant 3 to quadrant 1. So that's another indication of how we could tell that it's an odd function, is because its end behavior is diagonal. It's not the same direction. Same direction is only when it's even. And the last one is to determine whether it has point symmetry and whether the leading coefficient is positive. So the leading coefficient first is, let's look at our end behavior. Our end behavior is quadrant 3 to quadrant 1. And remember, for odd functions, quadrant 3 to quadrant 1 means the leading coefficient. I'm just going to use a short form for LC. The leading coefficient must be a positive value since it goes from quadrant 3 to quadrant 1. The last one is, let's take a look at whether it has any symmetry. So if we try and draw a line down the middle and we fold it over top, it's not going to match up, so it doesn't have line symmetry. If we draw a point directly in this middle here and rotate this part of the graph around, we see that it will eventually match up with this side of the graph, so it has point symmetry. Let's take a look at our second example here. So for this one, we can again count the number of turns. So we see that we have 1, 2, 3. So we have 3 turns. So at least we have to have a degree of 4, since it's 1 more than the number of turns. Our end behavior, and remember we can use a short form EB for that one. End behavior, we see that it goes from quadrant 2 to quadrant 1. And since it goes from quadrant 2 to quadrant 1, that's the same direction. They're both opening, both ends are opening in the up direction. So we know that it's even. We also know that it's even from our least degree. We know our least degree had to be a 4, which also tells us that it's even. So now that we know that it's even and our end behaviors are both up 2 to 1, for our end behavior to be up, that means our leading coefficient for even must be a positive. And then let's take a look for some symmetry. We see if we draw a line straight down here through that point in the middle, and we would fold it over top of that line, it's exactly the same on both sides. It's symmetrical on both sides of that line, so it has line symmetry. If anyone needs more time at this point to write this down, please pause the video. I'm going to move on to the next slide. Other examples that you should be able to do and that we've done in class together is if you're given specific information about a polynomial, you should be able to give me a quick sketch of it. Remember, with these ones, it's not about making it exactly perfect. And remember, there are multiple answers that would satisfy some of the specifications that I give. It's just making sure that your graph meets each specification. So let's take a look at some examples here. We have a third degree function with 2 turning points, a negative leading coefficient, and 2 x-intercepts. So we know for 2 x-intercepts it has to cross over our x-axis twice and no more than that. We know that it has 2 turning points. We know that it has a negative leading coefficient with a third degree. So because it's a third degree function, we know that it's an odd function. So third degree means that it's odd. And because it's odd with a negative leading coefficient, we know that our end behavior must go from quadrant 2 to quadrant 4. Oops. So we know that it's got to start in quadrant 2 over here and end in quadrant 4 over here, and that it only has 2 turning points. So let's take a look here. We're going to go down, back up, but it has to end in this quadrant, and it can't have another x-intercept, so it's got to bounce off the x-axis there and end up in this quadrant here. And remember, don't forget to add on your arrows. Mine's a little bit wonky in the middle here just because I'm drawing this on a computer, but yours should be a little bit better since you're doing it in pencil. But that's a graph that satisfies this. And remember, there are other options of ones that you could do. That is just one possible answer to that question. Let's take a look at our second one here. For our second one, we have a 6th degree function. It has 5 turning points, 6 x-intercepts, and a positive leading coefficient. So a 6th degree function, we know that makes it an even function since our degree is an even number of 6. We need 6 x-intercepts, so let's draw 6 points on our x-axis. 1, 2, 3, 4, 5, 6. We know that it's an even degree and it must have a positive leading coefficient. So because it's even with a positive leading coefficient, we know that it has to open up. And so that means we know that's quadrant 2 to quadrant 1. So we've got to start in quadrant 2. Remember, we always go from left to right, and end in quadrant 1. And we must have 5 turning points. So we start in this quadrant here, go down. Oops. Let's try that again. 1, 2, 3, 4, 5 turning points, and we end in our last quadrant here. And again, don't forget your arrows because it does continue up into those end quadrants up forever. Let's take a look at our last topic. So our last topic is the finite differences, so what we were talking about yesterday. Remember, finite differences, you've already calculated the first and second difference. We were just looking a little bit further at why we might calculate the third, the fourth, the fifth difference. Remember, from a table of values, to take our differences, to figure out what the finite difference is, we continue to take those differences. We took the third difference, the fourth difference, the fifth difference, and we continue to do that until our differences become constant, meaning that all of our distant difference values are the same. And depending on that, the number of times that we had to take the difference, remember it was dependent on the value of the degree of our function. So whenever our degree was a degree of 2, we only had to take the second difference. If we had a degree of 5, we had to go all the way to the 5th difference to get our differences to be a constant value. Remember, the other thing that we talked about is this formula here. We can figure out what the constant finite difference is if we know what the leading coefficient is, which is A, and if we know what the degree is, which is N. And remember, this exclamation mark here was called a factorial, and remember, it was just a button on your calculator. So we can calculate the finite differences based on this formula here. Again, remember, you need to know this formula. It will not be given to you, so make sure that you are studying this formula and that you know it for tomorrow. So let's take a look at some examples that I might ask in terms of asking you to calculate for finite differences. So for this one here, you're asked to determine what the constant finite difference is of the following. So you have this equation. So we need to figure out what the degree is first. So our degree here, we look for our highest exponent, which in this case is a 3. So we know we have a degree of 3. So we know that we would have to take the third difference to get our constant finite differences. Our leading coefficient, remember, is the number sitting in front of that variable with that highest degree. So in this case, our leading coefficient is -2. So to figure out our constant finite difference, we use our formula of the leading coefficient, -2, multiplied by our degree, and then it's our degree factorial. And remember, that's just something you type into your calculator. So you're going to have -2 multiplied by 3 factorial. 3 factorial is a value of 6. And then you have 6 multiplied by -2, which is -12. So your constant finite difference is a value of -12. Let's take a look at the second example. Again, we need the degree, which in this case, our highest exponent is a 4. So we would have to take the fourth difference if we were doing it with a table of values. Our leading coefficient then is a value of 3. So to figure out our constant, we take our leading coefficient of 3 and multiply it by our degree factorial, which is 4 factorial. So when we're calculating that out, that's 3 multiplied by 4 factorial is 24. So 3 multiplied by 24. So our constant finite difference would have a value of 72. Remember, the last type of example with this is that I could ask of you is to determine what the leading coefficient is if I give you what the degree is and what the constant finite difference is. So in this one, you're given the leading coefficient. We're trying to find the leading coefficient. You're given that the degree is 5 and that the constant finite difference is a -54. So we're going to use our formula that the constant is equal to our leading coefficient multiplied by our degree factorial. We know that our constant is -54. We're looking for our leading coefficient of A, and we know that our degree is 5. So let's figure out what 5 factorial is. 5 factorial is 120. And then to get A by itself, we need to divide by the 120. So we do -54 divided by 120 equals our A value. And then in this case, because it's a fraction, we can try and reduce that fraction. And if we reduce that fraction, we would get a value of -9 over 20. And that's by dividing both the top and bottom by 6. So that our leading coefficient then would be a value of -9, whoops, there we go, and -9 over 20. That is it in terms of concepts that we have covered for this first half of our unit. You'll notice on the last little bit of your handouts there that I have your format of your test. Remember, it'll be a very similar format as to your last test, but it'll be a slightly smaller since we only have half of our unit that we've covered so far. You will have multiple choice questions. There will be 7 of them. You will have some short answer questions. There will be 2 questions that are worth 4 marks. And then the rest will be long answer questions. There's 3 long answer questions and they're worth 3 marks. Remember, communication is evaluated throughout the test. That's on your legibility, your clear answers. Do I see clearly what steps you're following to get to your answers? If you just jump on answers and I can't clearly see a thought process, that's losing communication marks. That also includes any therefore statements and proper labeling on graphs. Remember, graphs, you need to have your labels of your x and y axis, and on this case, graphs, we don't have numbers on this one, so don't worry about that one. Just make sure that you have your x and y axis and the graph labeled. And that you have 3 marks of communication on this test. There are some review practice questions in your textbook that are good questions to go over. There aren't as very many in the textbook though, so I did include also a practice test that will get handed out to you. The practice test is a very good indication of the types of questions that you're going to see on your test, so please make sure you work through that practice test. If you have any questions about the practice test that you want to go over, remember you can come in at lunch tomorrow to see me before class to go over anything that you're struggling with before the test. And remember, another good indication of places to study is your notes and the homework questions that I've asked throughout the first part of this unit. I hope you guys have a great afternoon, and please make sure you're using your class time wisely to study and prepare for your test tomorrow.